In this section of Chapter 11, we're going to be talking about the alkylation of the alpha carbon. Remember, the alpha carbon is adjacent to the carbonyl. So remember, our alpha carbon is the carbon that is adjacent to the carbonyl, so that becomes our alpha position. If we have our groups on either side of the carbonyl, we would have two alpha positions. If we have an aldehyde, we would only have one alpha position. As we walk away from the carbon of the carbonyl, we continue to discuss those specific carbon atoms. So the second carbon out is what we would consider the beta position. But what you want to remember is that the alpha position has acidic protons. The hydrogens that are there are slightly acidic. So if we treat them with a strong enough base, we can actually get them to deprotonate. We do have to use very strong bases. Typically, hydroxide bases are not strong enough to do this, that we would need to do something like the hydride ion or the ammonium anion, the NH2-, in order to deprotonate that alpha position. So keep in mind that it does typically need to be a fairly strong base for that deprotonation to happen. So if we look at this reaction in terms of alkylating in that position, I'm just going to start off generically with an aldehyde so that we only have one alpha position, but please remember that this can happen with ketones as well, or with carboxylic acids, anything that has that alpha position. The first thing that we're going to treat it with is going to be some strong base, so I'm just going to use sodium hydride. That will be my deprotonation to get rid of the proton in the alpha position. From there, I'm going to use any kind of an alkyl halide. And then that anion that we generate after we have done the deprotonation will then react with the alkyl halide to give us an alkylated alpha position. So walking through the mechanism associated with this reaction, again, I'm going to show those alpha protons because that's what we're going to take advantage of. The sodium hydride, I'm going to take advantage of that hydride ion, and it is going to deprotonate one of those alpha protons for us. Remember, this leads us into our enolate anion. That enolate anion is stabilized through resonance, which is why those protons are going to be acidic. Because of that resonance stabilization that we have. The anion that we have generated can then react with the alkyl halide that we put into solution by once again attacking the electrophilic portion of the alkyl halide, driving off the halogen. So in this example, it now leads us to the alkylated aldehyde, as well as having the I- in solution as well. So now let's look at the regioselectivity. So this would be where we have a ketone and we have alpha hydrogens on either side of the ketone, and they are different. So looking at the regioselectivity of where we're going to produce that double bond if we have different alpha carbons around our ketone. One of the reagents that we can use is going to be lithium diisopropylamide, or abbreviated as LDA. And if we use LDA as our component, we're going to see that we are going to alkylate at the less substituted carbon atom. So lithium diisopropylamide is going to be our lithium, and then that is going to be paired with a sodium that has two isopropyl groups on it. So the nitrogen would have the negative formal charge, the lithium would have the formal positive charge. So if we look at this in terms of a structure, we have our nitrogen with two isopropyl groups that has an overall negative charge, and then it would be balanced with a positive charge. If you look at this compound, hopefully because of those isopropyl groups, you can recognize that it is a very big and bulky compound with those two isopropyl groups on it. So it will attack the less substituted carbon atom, or deprotonate that less substituted carbon atom initially, generating that to be the new nucleophile as we go through the alkylation process. One of the other options that we have is going to be the alkoxide base. So this is that RO- unit where we have basically deprotonated an alcohol. If we use an alkoxide base to deprotonate the alpha position, the alkylation is going to occur at the more substituted carbon atom. So these tend to be a lot smaller with the alkoxide base, so we will see a alkylation at the more substituted carbon atom. So let's look at a couple of examples in terms of this regioselectivity. So here's my ketone. The alpha carbon on the left has 2 alpha protons. The alpha carbon on the right only has 1 alpha proton, so they have different substitutions. So if I take this compound and I initially react it with the LDA, so the lithium diisopropylamide, followed then by my alkyl halide, I'm going to see a substitution or an alkylation at the less substituted side. So we will end up putting that carbon chain on the left-hand side of the molecule. But if I take and I do this with an alkoxide anion and react it with the same exact alkyl halide, what we will see is that my alkylation is going to be on the more substituted side. So we can really predict the regiochemistry of this alkylation depending on the initial base that we use to deprotonate that alpha position. So if we use the LDA, we will get the less substituted side being alkylated. If we use the alkoxide anion, that RO-, we will get the more substituted side being alkylated. So going back to kind of talking about this under kinetic or thermodynamic control, the LDA reaction is really what we call the kinetic control. The pKa of an alpha position is approximately around 20, depending on what else is in the compound. The pKa of our diisopropylamine is going to be equal to 38. So this is going to favor for us the weaker side. It's going to favor the enolate anion in that process. So it's really an irreversible reaction for us. So that's why it's going to be our kinetic control. If we look down at our RO- reaction, where we have alkylated the more substituted side, this is really what we would end up classifying as a thermodynamic control. Again, the pKa of our alpha carbon is about 20, depending on what else is in our compound, but the pKa of the alcohol, depending on what the R group is and what is there, is about a 17. So with this one, we really favor more the alpha carbon position. It is the weaker of the acids. So with this one, we're taking advantage of stability with this process, and that we are generating more carbon-carbon single bonds. So this is our thermodynamic control, because that initial reaction would go under equilibrium. So the driving factor for it is going to be the more stable compound. So next, let's look at the mechanisms associated with this process. So for the LDA reaction, we're going to be taking that diisopropylamide compound, and it is going to be deprotonating on the less substituted side. Again, this will lead us into that enolate anion that is going to be resonance stabilized. And then we have the protonated diisopropylamine. So from here, the carbanion that we just generated can react with the alkyl halide that we would have in solution. Again, remembering it is going to attack the electrophilic portion, driving off our leaving group. get us to our final less substituted alkylated product. The other one that we will be looking at then, if we're dealing with our alkoxide base, the RO minus will come in and now deprotonate the more substituted side. Which again, the enolate anion is stabilized through resonance. But going back and looking at our thermodynamic control, you can see that this is the more stable enolate anion because it is the more stable alkene that we have, since the alkene is more substituted, which is why it's thermodynamics, it's stability that is driving this process for us. And then we also have generated the alcohol. So then once again, once we have this enolate anion, it will come in and attack our alkyl halide that we will put into solution, driving off the leaving group. And we will see through that process we have the alkylation done on the more substituted side.